Please. Okay. So I'm going to start. My name is Victor David. I work with the team of Maxime Nibar, which is the team part of ARIA Technology that studies microscale modeling. And my presentation is going to be about the Scan360 package. I'm going to present to you a few slides about that. So just a little bit of context. So Scan360, the mission is to retrace and to reconstruct sources of greenhouse gases, which typically will be CH4, NO2, and CO2. And the way we do that is that we want to avoid having many sensors which are very costly. And instead of that, we're going to have one of these sensors moving around a site, and we basically reconstruct some fictitious sensors, allowing us to calibrate a dispersion model onto these sensors that we would reconstruct. So what you can see here on the right hand of the screen is typically a series of measurements that have been conducted on such a site. These measurements include concentration values, and through a series of algorithms, we are going to concatenate those values into a series of discrete sensors, which are not physical but fictitious. And these sensors then allow us to compare our results from our numerical model to these values in order to evaluate if our emissions have been calibrated correctly, or in the contrary case, if it still needs some more calibration. So the model that we use for this calibration is PMSS, which I think you should already know by now. And I'm going to talk about the three main steps of this approach. So in the first step, we receive the data from the on-site measurements, and there's a series of pre-processing steps that we need to go through, just so that our Python scripts and all can run correctly. We select a period of wind which is stable, because this is one important thing to know, is that we perform these calculations on constant meteorology, which means that we will have one direction and one wind speed. And for that reason, we only process the measurements which have been taken inside a certain stable weather domain. And once we have selected this data, we then proceed to the concatenation, which you just saw on the previous slide. And that leads us to step 2. In step 2, we will then construct the numerical domain. So basically defining all the sources, their location and their geometries. Then we also take a look at obstacles, if there are any in the region. And we will then define the domain's characteristics, such as the rugosity or the terrain height. And all of that leads to a numerical mesh, which we will then use for the dispersion modeling. And once we have performed the second step, we have defined a first guess for all the sources for the emission. Then comes step 3, in which we perform the actual simulation, and we then compare our results from the simulation with the concatenated sensors. And this allows us then to redo more simulation steps if needed, if we still need to adjust some emissions, or if the model seems to be calibrated, then we can extract the final emission values. Here's another real-life example of this concatenation process. As you can see, this is a I don't remember the word in English, but this is where you put the waste, basically, and there's some very important sources of methane. And on the left part, you can see all the measured data, all the little points that you can see. And these points are then concatenated, and you can see the concatenated sensors on the right side. And this is basically the step 3 that I just showed you. Once the model has run with the emissions that we had given it as input, then we can see if the model corresponds to the measured data. Now, this is not done visually, of course. This is all a data comparison behind it, but just so you can see if we identify some regions where it still seems to be some discrepancies, we can then adjust some sources in order to make the data stick better. And what's still important as well is to keep in mind that this model needs a lot of assumptions and a lot of simplifications. So we still need to keep in mind some information that the person who did the actual measurements on site might give us. For this example, we had a little area that was populated with some livestock present, which caused some additional emissions of methane, which we had not accounted for in the first step. So this kind of information can be useful as well. And typically what we try to achieve is an uncertainty level of 15 to 30%. So this is the difference between the measurements and the model. So that was the basic structure of Scan 360. And I'm now going to pass on to Bruno, but if later on you have some questions about this, I will be happy to answer.
Okay, thank you. So now we will talk about, oh, sorry. Now we'll talk about Paris. Now we'll talk about SIMPAC more precisely, and actually for some reason, the destiny of SIMPAC is highly related to Lubrizol, which is a high-risk chemical plant in Rouen. So this is, sorry. This is a map. Here is Rouen, here is Paris. And in 2013, a leak of malodorous gas was smelled about 100 kilometers from the site, notably in Paris or in the UK. And this incident led to the development of the first SIMPAC platform for Atmosud as part of the creation of a rapid intervention force among the different air quality association in France. There was then a second incident, actually a fire at the chemical plant in 2019, and a thick plume of black smoke was formed and reached more than 20 kilometers. And this led to the deployment of the platform to 2 additional air quality associations, namely Atmo Normandie first and now Atmo Grand Est. So SIMPAC is a platform that allows the configuration of the dispersion calculation by people who do not have as training in modeling the atmosphere dynamics, and results are synthetic, easily exploitable, and understandable in context of emergency. So I will try to be short, but accessing the SIMPAC platform is possible through the connection of a web server. The user is then redirected to a dashboard here of its dashboard corresponding to its platform. So Atmo Normandie here or Atmosud. And the dashboard is organized by project, each project corresponding to modeling of meteorological modeling or dispersion modeling carried out. The very simple sketch here is a schematic of the architecture, general architecture of the platform. So here is the web browser of the used by the user, and the user connect to a web server currently on AWS that then exchange information to a computational server that carries out the simulation on a virtual machine in order to simplify both the installation, the deployment, and update of the computational server from one machine to the next. The modeling part is done using PMSS that you all know very well. The only point I want to mention here, so PMSS is pSwift for the atmospheric modeling, and there is different available option for the meteorological modeling, namely using one or more meteorological station or a large-scale model like WRF or MM5, or a uniform and constant user-defined condition. And this is actually important because large-scale models are not always very precise at local scale, in particular, or for example, near the coast. But they can still be used, and they can still be very interesting to perform forecast of what could be the dispersion. So we use PMSS, atmosphere with pSwift, dispersion with pSpray. I don't really have a lot of time to explain, but two different simulation are possible in the SIMPACT platform. So direct simulation or inverse simulation, meaning that the pollutants are transported, advected by the mean wind to mean wind, to which we add some fluctuation in order to represent the turbulence. In a Lagrangian model, the computational time increases linearly with the number of numerical particles in the calculation domain, and this is also why in a user-friendly platform we decided to vary this number with the chosen configuration, and it goes from 1 particle per time step to only obtain an indication of the plume direction up to 600 particle per time step, where the user can define the species and the emitted flux for the different sources. Different sources also because different type of sources are possibly defined, so point source, manually defined, or use from a pre-available database. The user can also define through, maybe this is not really visible here, but you have a triangle. The user can also define surface sources using the computer mouse through the web interface. And another one that I will not go into detail, but the user can also define the source term of industrial fires. This is not my expertise, but actually to develop that, we followed the INERIS methodology, which are the experts on that subject, and others in France. the last minutes that I have, I hope, is I will try to present one of the recent implementation in the SIMPAC platform. So adding a new source term and adding a fire forest propagation model. Yeah, there should be fire forest or propagation model in SIMPAC. And to do that, we implemented the Farsight model. So it's developed by a US lab. Farsight model follows a vectorial approach, meaning that the fire is defined through a set of 2D vertices, and the number of vertices increase as the fire expands or as the fire develops over time. And at regular, so this is sketched here, at regular intervals, the expansion of the fire polygon is determined by calculating the velocity and the direction of propagation for each vertex. When the implementation was carried out, there was validation test case. So here it was the fire that occurred in Martigues. Martigues is a city in the south of France. Here, the fire started at 3 universal time, ended here at the sea at 19 universal time. And here is the sketch given by the firefighters of the red arrows, the propagation of the fire, and in blue, the sensitive areas and the places that where the firefighters actually work to prevent or limit the propagation of the fire. Okay, like every numerical model that I know, but I don't know everything. So every numerical model that I know, there's always a lot of parameters. Among the important ones, there was the humidity of the fuel. So the humidity of the fuel is the ratio between the amount of water contained in the wood divided by the mass of the wood without that water. And this humidity of the fuel strongly influence the fire spread. And this is visible here, sorry again. So this is the reference test case. The fire started here, and here you have diesel line in green, let's say, green at different time steps. So the fire front at different time steps. So this is the reference case, and on the right, you have a simulation where we increase the fuel humidity by 5%, and you have the fire front that the development of the fire, which is really reduced. Okay, so when the implementation was finished, carried out, we tried to reproduce this Martigues fire, and fire started here at 5, ended here at, you can read it here, ended here at 19 near the sea, and the total we used to model the atmospheric condition, 2 med station, Marignane and Istres. The total cost of the simulation is 9 minutes for Farsight plus P-spray. This was also something important to say, because in case of emergency, you don't have a lot of time to carry out those kind of simulation. And comparison with the real case is not that bad. Difference can partly be explained by the fact that the work of the firefighters to limit the fire propagation were not considered at this stage in this implementation. During the visualization through the web browser, we added, here in blue, we added the non-burnable areas, so obviously the sea, but also the dense urban areas, which are defined for the fire propagation model as non-burnable. So this was done in Simpax. So the idea at the end is to model dispersion. And so here is a visualization of the smoke plume when we emit on simply tracer with an emitted mass of 1 kilogram per hour at the fire front, so evolving with time. And with this, I think I'm done. So thank you very much. I hope I was clear. And now if you have any question regarding Scan 360 or Simpac, please, we'll try to answer. Thank you.